Hey guys, welcome back to my channel. How's it going? Today we're diving into Bayes Theorem, a cornerstone of probability theory that lets us update our beliefs based on new evidence. It finds its application in many areas from medicine until the science, research, and even machine learning. So it may sound a bit complicated. I think it is better to get started with a specific example. Now let's imagine this. Suppose there is some kind of rare disease, and 1% of people on our planet have this disease. So the likelihood of this disease, let's say, just a likelihood of the disease equals to 0.01. A test for this disease exists, and it is 99% accurate if you are infected. It's 99%, so this is about 0.99. If you are healthy, the accuracy of this test is 95%. So let's say this is not even the likelihood, let's say the accuracy. The accuracy of this test, if you actually seek, accuracy of the disease is 99%, and accuracy if you are healthy, is 95%. So this is around 0.95. So in this case, a test must result in the negative. In this case, it has negative with accuracy 95. And in this case, it must say positive, since you are actually sick, with 0.99 or equivalently 99% of accuracy. So let's suppose a scenario that you test positive. What's the probability you actually have the disease? Well, intuitively, you might think this is around 99%. But Bayes' theorem reveals a shocking truth here. So first, let's consider the probability basics. Let's recall the conditional probability that we learned in our previous videos. The probability of A given B is the probability of A given that B has already occurred. So for our specific example, the probability that you have a disease is 0.01. The probability that you test positive, given that you have disease, is 0.99. The probability that you have a positive test, given that you don't have a disease, no disease, is 0.5%. Why it is 0.5%? Because it is essentially 1 minus 95%, which is just 0.05. This is basically a false positive rate. Now we would like to gauge what the probability of having a disease in case we have a test positive. Well, in terms of traditional approach, if we ignored conditional probabilities, we might naively assume the test is 99% accurate, so I'm 99% sick. But this ignores critical factors. The disease is rare, only 1% prevalence. And the second factor is that we have false positiveness. Statistically speaking, 5% of healthy people test positive. So Bayes' theorem fixes this by balancing prior knowledge and new evidence. So now let's derive the formula for Bayes' theorem based on our specific example. Let's start with a definition of conditional probability. For the probability of having the disease, given that we have a positive test, will be essentially equal to the probability of having a disease and at the same time having a positive test over the probability of having positive test. Now we can actually take another look at the numerator. We can expand our numerator. What is that? It is a disease and at the same time positive test. This can be written as the probability of having a disease times the probability of having a positive test, given that we have a disease. It is essentially the converse version of the having the disease based on the positive test. Now we can say that probability of having disease and positive test equals to the probability of having disease multiplied by the probability of having the positive test, given that we have a disease, over the probability of having the positive test. Moreover, based on our previous lessons, we know that probability of an event A will be equal to the probability on event A1 times the probability of event A given the A1 plus the probability of an event A2 times the probability on event A given the A2. If one of these events, A1 or A2, may result in the event A. So we already considered this formula in our previous video. Please get back to our previous video and recall this formula. And let's expand our probability of positive test, which equals to the probability of having a disease times the probability of having a positive test, given that we have a disease, plus the probability that we don't have a disease times the probability that we have a positive test, given that we don't have a disease. So in this case, our A1 is disease, A2 is no disease. Our A is positive test. So we calculated the probability of positive test based on the aforementioned formula. Now let's take a look at the final result of having disease given that we have a positive test. If we calculate this formula, we'll get as a result the following fraction: 0.001 times 0.99 plus 0.99 times 0.05, which approximately equals to 0.167, which is about 16.7%. So Bayes' theorem shows that rare disease dominates the math, even with accurate tests. Let's formulate the formal statement of Bayes' theorem. If we have lots of mutually exclusive events, like no disease or having a disease, like in our previous examples, but in our case we have n mutually exclusive incompatible events, and one of these events may result in the occurrence of the event A, possibly result in the occurrence of the event A, which is a subset of the sample space. In this case, we can derive the formula that the probability of some kind of event AR given the event A, in our previous example it was a positive test, equals to the numerator, the probability of event AR times the probability of the event A given the AR. Remember the previous example, this is having a disease, this is like having a disease, this is like the having a positive test. It can be symptoms or anything else. And in our denominator, we have the probability of AJ times the probability of A given AJ, where J takes on the values from 1 until the n. So this is just the sum of all possible probabilities here. The probability of AJ times the probability of A given AJ, which equals to probability of A1 times the probability of A given A1 plus the probability of A2 given times the probability of A given A2, and like this, and following this pattern until the probability of an times the probability of A given an. So this is it. We already considered this formula in our previous video. Now let's take a look at the second example. Suppose we have a factory with 3 machines, where each machine produces widgets. Machine 1, the first machine, has 50% of output, and 2% of them is defective. Machine 2 has 30% of output, 3% of them are defective. And machine 3 has 20% of output, 5% of which is defective. Now, if a widget is defective, what's the probability it came from the machine 3? Let's denote that our machine produced a defective widget as D. This is an event of producing a defective widget. Now let's denote as the probability of M3 given this is defective is the probability it came from the machine 3. We can essentially calculate the total probability of the event D here. So to calculate the total probability of event D, and this total probability that we have a defective part equals to summation of probabilities Mj times the probability this is defective given this is a machine Mj, where J takes on values from 1 until the 3. P of Mj is the percentage of the outcome. So for the first machine it will be 0.5, for a second machine it will be 0.3, for the third machine it will be 0.2. Now the probability this is a defective given a specific machine, machine M1, it will be 0.02. The probability this is defective for the second machine equals to 0.03. The probability this is defective for the third machine equals to 0.05. Now we can just calculate the total probability for defectiveness, which equals 0.5 times 0.02 plus the following expression plus 0.05 times 0.2. And we can also calculate the numerator here, and numerator equals to the probability, if you take a look carefully at our formula, that will be the probability of M3 times the probability of having a defective part given it came from the machine M3. So having the output from the M3 times the probability having a defective part which came from the machine M3, which equals to 0.2, which goes from here, times 0.05, which goes from here. So now we just need to compute this. We have the likelihood it came from the machine M3, given this is a defective, which equals to 0.2 times 0.05 over our total probability 0.5, 0.02 plus 0.03, 0.3 plus 0.05 times 0.2, which will be equal approximately to 34.5%. Even though machine 3 has the highest defect rate, it only contributes to 34.5% of defective widgets due to its smaller output. Bayes' theorem reverses the direction of inference. Instead of asking what's the effect of a cause, like in case when we need to find the positiveness of our test based on if we have a disease or not, we ask ourselves what's the cause of an effect. So we essentially calculate likelihood of having a disease based on the positive test. So we're asking ourselves about the cause. We're calculating the probability of having a specific cause based on the output, based on effect. And this makes it indispensable in the fields like medicine, machine learning, and even the law. Bayes' theorem is a powerful tool for reasoning under uncertainty, and we're going to cover more complicated examples later on in this course and in other different courses. But for now, that's all I had for this video, and I hope you found this helpful. If you have any questions, or if you still do not understand what the Bayes' theorem is, please leave the comments in the comment section below. I'll try to do my best to help you. We also have our Discord community. You can find the link in the description section below. And I wish you all the best in your learning journey. And as always, see you in the next episode. Bye.